Hey folks, my name is Nathan Johnston. Welcome to lecture 37 of Introductory Linear Algebra. In today's class, we're going to start learning about something called eigenvalues and eigenvectors of a matrix. And this is a really exciting topic because it's sort of the start of the punchline of this course, okay? It ties together everything that we've been learning about. It ties together the determinant of a matrix, inverses of matrices, subspaces, bases of subspaces, the null space of a matrix. It tells us why we've been learning about all of these things, okay? The reason we've been learning about them is so that we can compute eigenvalues and eigenvectors and do really neat things with them, okay? So this week we're going to be learning about eigenvalues and eigenvectors themselves, and then next week we're going to learn about, well, what can you do with eigenvalues and eigenvectors, or at least a taste of what you can do with eigenvalues and eigenvectors. All right, so what is an eigenvalue and what is an eigenvector? Well, sort of the idea behind them, before we get to sort of the full proper definition, the idea behind them is think about how nice diagonal matrices are, okay? So for example, if I had this diagonal matrix that just has 1/3 and 2 as its entries, then this matrix, it sort of plays very well with the standard basis vectors. So remember, E1 and E2, those are the vectors that have a 1 in the first entry and a 1 in the second entry respectively, and then zeros elsewhere. Okay, and if you multiply a diagonal matrix by these standard basis vectors, well, it's the same as just doing a scalar multiplication. For example, if I do this matrix A times E1, the vector that has a 1 in the top entry and 0 down below, what's going to happen is you're going to pick off this 1/3 up in the top and still 0 down below. So it's multiplying that standard basis vector by A is the same as just multiplying it by a third, the first diagonal entry. And similarly, multiplying the second standard basis vector by A is the same as just multiplying it by 2, the second diagonal entry. Okay, so sort of geometrically what's happening is this diagonal matrix, like remember linear transformations or matrices, they sort of stretch and distort this unit square grid into a parallelogram grid in general. But if the matrix is diagonal, what's happening is the direction of these vectors is not changing. E1 and E2, they're not changing direction, they're just getting scaled. So it doesn't turn into a parallelogram grid, it's just sort of a distorted square grid. It's getting stretched by independent amounts on the x and y axes, so it's turning into a rectangular grid, and not even a rotated rectangular grid. It's really just getting stretched in those two directions. Okay, and this is sort of what we would like to happen with linear transformations in general. It doesn't happen in general, but we would like something like this to happen in general. And that's the idea behind eigenvalues and eigenvectors. What we want to do is we want to find a basis in which, well, things are just getting stretched. They're not getting, rotated and moved. All right, so that's the idea behind eigenvalues and eigenvectors. Okay, so that sort of motivates this definition here. Suppose you've got any old square matrix. Okay, it doesn't have to be diagonal anymore, just any old square matrix. Well, we say that some scalar lambda is an eigenvalue of A if there's a non-zero vector V such that A times V equals lambda V. Okay, and this non-zero vector V here is called the eigenvector corresponding to the eigenvalue lambda. Okay, so they sort of, like eigenvalues and eigenvectors, they come together, right? And if you have one of them, you must have the other one. If you have an eigenvalue lambda, there's got to be a corresponding eigenvector V. And if you have an eigenvector V, there's got to be a corresponding eigenvalue lambda. And what it is this vector V, that's the vector that's just getting stretched. It's not getting rotated at all. And the eigenvalue lambda is how much is it getting stretched by, okay? So if we go back up to this diagonal example up above, for this matrix here, for this diagonal matrix, the eigenvalues are 1/3 and 2, right? Those are the stretching factors. And the corresponding eigenvectors are E1 and E2. Those are the vectors that are just getting stretched by A. Other vectors might be getting rotated around and moved and changed their direction, but these two vectors are special. They're just getting stretched. So those are the eigenvectors. All right, so let's start looking at non-diagonal matrices. Okay, let's start asking the question, how could I find eigenvalues and eigenvectors for matrices that aren't diagonal, so for uglier matrices? And so we're going to start one piece at a time. Let's suppose that we were given a particular vector v equals 1, 1, okay? And we're told ahead of time, this is an eigenvector, or maybe just probably that it's an eigenvector. Let's verify that it's an eigenvector, and let's find the corresponding eigenvalue. Okay, so how could we do that? Well, we just go back and look at this definition here. So I'm given A, right? A is this matrix here. I'm given V, and I'm given the V over on that side too. So I mean, all I have to do is I have to compute this product A times V, and if the result is a multiple of V, then yeah, it's an eigenvector, and I'll be able to just read off what the eigenvalue is. It's whatever that multiple is. So let's do that. Let's compute A times V and see what we get. All right, so here's A, here's V. I do my matrix multiplication, and I get the vector 3, 3, and then I squint at that really hard. Is 3, 3 a multiple of 1, 1? And yeah, it is, right? It's just 3 times that vector v. It's 3 times 1, 1. So our conclusion then is yes, v really is an eigenvector. Okay, and what's the corresponding eigenvalue? Well, it's 3. It's how much was that vector v stretched by? Well, stretched by a factor of 3. So the corresponding eigenvalue is 3. Geometrically, what's happening here is this linear transformation is taking space and distorting it into some parallelogram grid. And most vectors are getting their direction changed when this happens, okay? So when you apply A to two-dimensional space, most vectors are getting their direction changed. For example, E1, it's not pointing off to the right anymore. Now it's pointing sort of upright. And similarly with E2, it's not pointing in the same direction. So those two vectors are not eigenvectors. But this vector V here, that one's special. Okay, because what happens to it is, well, it's still pointing in the exact same direction after I apply A to it. It's just longer. How much longer? Well, 3 times as long. Okay, so yeah, most vectors change direction, but your eigenvectors don't. That's what makes them special. That's why we like them. Okay, so for eigenvectors, multiplication by a matrix is the same as just scalar multiplication by the corresponding eigenvalue. All right, so the example that we just went through up above was a little unrealistic. In it, we were given the eigenvector and asked to find the eigenvalue. In the real world, you're not given either of them, okay? You're just given the matrix and told to find the eigenvalues and eigenvectors. So how do you do that? How do you find both if you don't know either of them? All right. The typical procedure is sort of to work in 2 steps. First, find the eigenvalues, and then find the eigenvectors based on the eigenvalues. Okay, so let's go through these 2 steps one at a time. Let's think about how we could find the eigenvalues of a matrix if we don't know the eigenvectors ahead of time. Okay, so we know A in this equation that we're trying to solve. We know A, but we don't know V and we don't know lambda, and we're trying to find the valid choices of lambda. How can we do that? Okay, so what I'm going to do with this equation here is I'm going to start off by moving everything over to the left-hand side. Okay, so I'm just going to subtract lambda v from both sides, and then I get this equation here. Okay, and remember what I'm trying to do is I'm trying to solve this. Okay, I want to be able to figure out what lambdas are possible, what lambdas can lead to this having a solution. Okay, a non-zero solution. Okay, these eigenvectors v have to be non-zero. All right. Well, what I'm going to do from here is I'm going to factor this left-hand side, okay? Because notice, hey, I've got a v on the right and a v on the right. I can factor that, okay? And if I factor that, what happens is I get a times v, so I can factor out an a, and I get lambda times v, so I can factor out a lambda. Be careful, though. You have to factor out a lambda times the identity here, okay? And the reason for that, well, let's think about what the alternative would be. Maybe the thing that you want to do, maybe sort of your gut reaction about how you would factor that is something like this. Maybe your first instinct was, okay, if I factor this, I factor out an a, and then I factor out a minus lambda. Okay, and the reason that doesn't work, the reason you can't do that is because this thing here, a minus lambda, that's not a thing. Okay, this is a matrix, and you're subtracting a scalar away from it. Okay, and what does that mean? Matrix minus scalar is not a thing. I can add or subtract matrices from each other, so I can do matrix minus matrix, but not matrix minus scalar. Okay, so this is not even a thing, so don't ever write something like this. The correct version is up here, and if you want to convince yourself that this is really correct, I mean, notice that, hey, I've got matrix minus matrix, so that is a thing. Okay, and also, if I multiply this back out, well, I get AV, good, I get the AV, and I get minus lambda IV, and the I times V just becomes V, so I get minus lambda V. Okay, so this is sort of the correct way to factor out a scalar times a vector, throw an identity matrix in there just to make it actually work. All right, and this expression here, this is equivalent to saying that this vector V, it's in the null space of this matrix, right? That's just the definition of the null space. The null space of a matrix is the set of solutions of that matrix times V equals 0. Okay, so this is all equivalent to V being in the null space of A minus lambda I. Okay, now remember, what are we trying to solve here? We're not trying to find V, but rather we're trying to find the lambdas that make this solvable. Okay, so in other words, we're trying to find the lambdas that make there exist at least one non-zero vector in the null space. Okay, well, how can we find when there is at least one non-zero vector in the null space? Well, that's exactly the same as saying that the dimension of that null space is bigger than 0, right? There's a non-zero vector in there is the same as saying is that it's at least one dimensional. In other words, the nullity of this matrix here is at least one dimensional. which is equivalent to saying that this matrix is not invertible, right? Remember, we went through all these characterizations of invertible matrices, and one of them was a matrix is invertible if and only if its nullity equals 0. So a matrix is not invertible if and only if its nullity is bigger than 0. Okay, and then now think about another characterization of invertible matrices. Well, another one was that a matrix is not invertible if and only if its determinants equals 0. Okay, so all of this junk, okay, we've traced through a big long argument here that is now shown that, hey, you can solve the equation AV equals lambda V if and only if the determinants of A minus lambda I equals 0. Okay, and this is good now because we have explicit formulas for the determinant. This is the type of thing that now we can actually solve. We can figure out what lambdas can actually be from this equation here. We've sort of hidden the v's. We don't have two unknowns, lambdas and v's anymore. We just have this one unknown, lambda. Okay, so now this is finally the type of equation that we can actually solve. So let's go through an example. Let's find all the eigenvalues of some matrix using this determinant of A minus lambda I equals 0 equation here. All right, so how do we do this? Well, start off, set that determinant equal to 0. This is always going to be our first step when we're finding eigenvalues. Okay, and now what am I going to do? Well, let's just plug in what we know. What is A? It's this matrix here. Okay, and then I'm subtracting lambda times the identity. In other words, I'm subtracting lambda from the diagonal entries, right? This 1 up in the top left becomes 1 minus lambda, and 4 in the bottom right becomes 4 minus lambda because I'm subtracting off lambda times the identity matrix. And the off-diagonal stuff just stays the same. It's still just 2 and 5. Okay, now I want to compute the determinant of a 2 by 2 matrix. Hey, I've got explicit formulas for that, right? For a 2 by 2 matrix, it's the product of the forward diagonal minus the product of the backward diagonal. So it's 1 minus lambda times 4 minus lambda minus 2 times 5, in other words, minus 10. Okay, and I want to figure out what lambda is, right? I'm setting this whole thing here is set equal to 0. How do I figure out what lambda is? Well, I've got to factor this entire polynomial. Like, this is actually a quadratic polynomial, right? Okay, so maybe the first thing that I'm going to do is I'm going to expand it out. Okay, and when I expand it out, like I multiply these parentheses together and then I subtract 10, I get this here. And now I'm going to factor it. Okay, I want to find two numbers that multiply to minus 6 and add to minus 5. Well, minus 6 and 1 do the job. Okay, so this is my factorization of that quadratic polynomial. All right, so what's that tell me? Well, remember, this equals 0, and the only way that can happen is if lambda equals 6 or lambda equals minus 1. Okay, so those are my eigenvalues. Okay, these are the values, lambda equals 6 and lambda equals minus 1. Those are the values that make this determinant 0. Those are the values that make A minus lambda I not invertible. That matrix is invertible for every other value of lambda. Those are the values that make there be at least one non-zero solution, V, to that equation there. Okay, those are the eigenvalues. All right, step 2. Now that we know what the eigenvalues of the matrix are, let's find the eigenvectors associated with each eigenvalue. And you have to be a little bit careful here. Okay, remember, like, eigenvalues and eigenvectors come in pairs. So what that means is for each eigenvalue you found, there's going to be corresponding eigenvectors. And then for the other eigenvalues that you find, there's going to be corresponding eigenvectors. Okay, so it's not just, hey, what are the eigenvectors of this matrix? It's, hey, here's a particular eigenvalue of this matrix. Find me the corresponding eigenvectors. Okay, so like there will be different eigenvectors for different eigenvalues. All right, and the way that we solve this, well, fortunately, finding eigenvectors, now that we know the eigenvalues, is fairly straightforward, okay? It's just doing things we already know how to do. It's just solving linear systems, okay? Because again, if we just go back up, we showed that, hey, this eigenvalue eigenvector equation is the same as A minus lambda I times V equals 0. But hey, we know A, we know lambda, so we know this whole matrix over here, and we're just trying to find the V's. That's a linear system, okay? Find the V's that are in the null space, okay? Solve a linear system. All right, so let's do this. Let's find all of the eigenvectors of this same matrix, okay? So this matrix A is the same one from the previous example. Okay, so what we do, first step, remember what your eigenvalues are, okay? We showed that minus 1 is one of the eigenvalues and 6 is one of the eigenvalues. Work with them one at a time. So let's start off with lambda equals minus 1. Okay, we want to solve this equation here for V. Okay, so just plug in the eigenvalue you know. Plug in the value for lambda. It's minus 1 this time, so be careful of your double negative. It's minus 1. It becomes plus 1 times the identity. All right, so this is the linear system that you want to solve. Okay, so let's throw that into augmented matrix form and solve it. So what you do, take your matrix A, and I'm adding identity to it. So add 1 along the diagonal, it becomes 2, 5 along the diagonal, and the off diagonal doesn't change. And you'll notice, like you can sort of see from inspection in this case, because it's just 2 by 2 and simple enough, you can see that this matrix is not invertible. That's what makes it actually an eigenvalue. That's why this is going to work out. All right, solve this linear system now. So now I just do my row operations to solve that linear system. And now I'm down in reduced row echelon form. Okay, this is my reduced row echelon form. Find all solutions of it. Hey, one of the columns is leading, one of the columns is free. Okay, and remember these columns, they correspond to the different entries in V. Okay, so the second entry of V, V2, is free. Okay, there's no leading entry in the second column. Okay, so that means I can write the other entries in terms of that second entry V2. Okay, and in particular, V1 plus V2 equals 0. Rearrange that, you get V1 equals minus V2. Okay, and then if I return and write that in vector notation, right, because I want to figure out what the vector V is, what this eigenvector V is. What that tells me is the eigenvectors V all have this form here, right? What is V1? Well, it's minus V2, so that's the first entry is minus V2. And what is the second entry? Well, the second entry is free, so it just is itself, it's V2. Okay, and typically what I'm going to want to do is I'm going to want to factor that. Okay, always, 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 when you're writing a solution set of a linear system in terms of the free variables here, you're always going to be able to factor those free variables out. Okay, so I see there's a V2 in each of the entries, factor it out, I'm left with a -1 and a 1. Okay, so in other words, the eigenvectors associated with lambda equals -1, they're exactly the multiples of this vector -1, 1. All right, let's go to the other eigenvalue now, okay? You have to do the same calculation, but now for the other eigenvalue. So your setup's the same though, okay? A minus lambda IV equals 0. This time I'm plugging in lambda equals 6 though. Okay, I'm checking the other eigenvalue. All right, and what's the augmented matrix look like this time? Well, again, I'm starting with this matrix A. Now I'm subtracting 6 off the diagonal entries. So 1 becomes -5, 4 becomes -2, and the off diagonal entries don't change. Do your row operations to get it down at least into row echelon form. All right, so there we go. Now I'm in row echelon form. And what are my leading and free variables? Well, leading variable V1, free variable V2. Okay, so V2 is free. I'm going to be able to get V1 in terms of V2. Okay, and in particular, let's see, this says -5 times V1 plus 2 times V2 equals 0. Okay, so just rearrange things so that's in the form leading variable equals something in terms of free variable. Okay, so this time, if I leave V1 on the left-hand side, move V2 to the right-hand side and simplify, I get V1 equals 2/5 times V2. Okay, so my eigenvector looks like this. What is V1? Well, it's 2/5 V2, so that's my first entry. And then what is V2? Well, V2 is free, so it's just itself. Okay, so these are what my eigenvectors look like. Again, I can factor out my free variable V2, and I'm just going to get V2 times this vector 2/5 1. Okay, so again, my eigenvectors, every multiple of this vector 2/5 and 1 is an eigenvector. Okay, all multiples of that, all non-zero multiples of that anyway, are eigenvectors associated with the eigenvalue 6 of this matrix. Okay, and one really nice feature of eigenvalues and eigenvectors is that they can help us understand what a matrix sort of looks like. Okay, and what I mean by that is, let's try to illustrate this matrix up above. Okay, this matrix A that we just worked through in the previous 2 examples. Okay, so what was it? It was 1, 2, 5, 4. Geometrically, what's that matrix look like? Well, we could draw our usual picture where we have like the unit square grid with one of the sides is E1 and the other side is E2. But if we do that and we try to visualize what A does to it, it just sends them off to some other place and we get some parallelogram grid. And it's maybe not all that illuminating. It's a little bit more illuminating if we look at what happens when, instead of starting with the unit square grid, what if we start with an eigenvector grid? Okay, so what if we start off with a parallelogram grid whose sides are made up of the eigenvectors that we just computed? So remember, corresponding to this eigenvalue -1, we found -1, 1 as one of the eigenvectors. Okay, so I'm going to draw that vector on here. Okay, and then the other eigenvector that we found was 2/5 1, so I'm going to draw that on here as well. Okay, and I mean all multiples of these are eigenvectors as well, so I didn't have to choose this like 2/5 1. I could have chosen like a longer version of it. Doesn't matter. Okay, just pick one of the eigenvectors associated with each eigenvalue. Okay, and now I'm going to ask, okay, what's A do to this parallelogram grid? Instead of what's it do to the unit square grid, what's it do to this parallelogram grid? Okay, and because the sides of this parallelogram grid are eigenvectors, they're not getting rotated, their direction is not getting changed, they're just getting stretched. Right? This side here, this minus 1, 1, it's getting multiplied by the eigenvalue minus 1. So it's just flipping direction. It started off over here, now it's going to be down here, but it's along the same line. Okay, and similarly, V2 here, this eigenvector, it's getting multiplied by 6, the associated eigenvalue. So it's just going to be in the same direction, but a whole heck of a lot longer. It's somewhere up there. Okay, and the resulting parallelogram grid, well, it's basically like it hasn't gotten distorted, really. It's gotten stretched independently along its two different axes, or its two different sides, maybe. Okay, but it hasn't been rotated. It hasn't been skewed. Okay, so sort of the geometric picture, even though you're starting with a parallelogram grid instead of a square grid, the geometric picture is a lot easier, right? All that's happening is sort of these parallelograms, they're getting 6 times as long in that direction, and they're mirroring in that direction. In this particular example, for this matrix here, associated with every eigenvalue, there wasn't just one eigenvector, but rather there's a whole line of eigenvectors, right? We said that, hey, every multiple of some vector was an eigenvector. And then for the other eigenvalue, also every multiple of this vector is an eigenvector. So we got sort of an entire line of eigenvectors. Something similar to this happens in general, okay? And the reason is, remember, how do we calculate eigenvectors? Well, we compute the null space of a certain matrix, right? We compute the null space of A minus lambda I, and that gives us the set of all eigenvectors associated with lambda. Okay, well, the null space of a matrix, that's a subspace, right? Okay, so it basically is. It's a line going through the origin, or it's a plane going through the origin, or it's a higher dimensional similar sort of thing going through the origin. It's a subspace. Okay, and now we're going to give that subspace a name. Okay, we call it the eigenspace associated with a particular eigenvalue. Okay, so suppose you've got some square matrix, so it makes sense to talk about eigenvalues. Let lambda be some eigenvalue, and then what we do is we say that the set of all eigenvectors corresponding to that particular eigenvalue, we say that's the eigenspace of lambda for this matrix, okay? And then one minor technicality is that we have to throw the 0 vector into that set to really make it a subspace, okay? Remember, by definition, the 0 vector is not an eigenvector, okay? It's never an eigenvector for any matrix, okay? So technically speaking, the set of all eigenvectors is not quite a subspace. It's because it's got that hole punched out at 0. We just sort of patch up that hole so that it really is a subspace, okay? Now, the reason for thinking about in terms of this is going to be highlighted by the next example, okay? Instead of describing all eigenvectors associated with a particular eigenvalue, what we typically want to do is just give a basis of the corresponding eigenspace, because that's sort of a minimal description of all eigenvectors, right? Just like in this previous example, I mean, we could say, hey, the set of all eigenvectors is the set of multiples of minus 1, 1, but now that we know that, you know, eigenspaces, sets of eigenvectors are always subspaces, we can just say, oh, well, its basis is this vector here. Okay, and similarly down here, for lambda equals 6, rather than always saying, oh, it's a set of all multiples of 2/5 1, now we can just say, okay, well, it's the subspace that has basis 2/5 1. Okay, and this becomes really important as these eigenspaces get bigger and bigger. Okay, so let's go through an example now with a bigger eigenspace, okay, with an eigenspace that isn't just a line, it's going to be something bigger than that. All right, so let's find all eigenvalues and all eigenvectors of this matrix here, but we're not going to say, hey, here are all eigenvalues. We're going to say, here's a basis of the eigenspaces. Okay, so same setup as before, though. The way that you find the eigenvalues, that's our first step, is find the eigenvalues, is you set determinants of A minus lambda I equal to 0. Okay, and when you do that, what you're going to get is, well, again, you're subtracting lambda off the diagonal, and you're leaving the off-diagonal entries alone. Okay, so the minus 3, 3, 3, that all stays the same. The 0, 0, minus 2, that all stays the same. And the diagonal entries just get a lambda subtracted from them. And then because this matrix is 3 by 3, we have an explicit formula, right? Product of the diagonal entries, and then the next forward diagonal is going to be 0, and then the next forward diagonal is going to be 0 as well. Okay, and then you have 3 backward diagonals that you've got to subtract off. So 2 minus lambda times 3 times minus 2 subtracted off. And then the other 2 backward diagonals are both 0. Okay, because they both have at least one 0 in the product. Okay, so that's our determinant, and we want to set that equal to 0. Okay, so it might be really tempting to just expand it all out and then factor the whole thing. Okay, but depending on what you've done in previous courses, that might be really, really hard actually. Certainly you can expand it all out, like you can multiply all these brackets out, and this time you'll get a cubic polynomial in lambda, a degree 3 polynomial. Okay, but then the next step of factoring it, right, finding the roots of that polynomial, depending on your background, that might be really, really hard. You might not have learned how to do something like that yet. So I'm going to do a little bit of a trick here. I'm going to notice that, hey, I've got a bunch of zeros, just forget about them. And then I've got a couple non-zero terms. And in each of the non-zero terms, I've got a 2 minus lambda. Okay, so I'm not going to multiply out that 2 minus lambda, because remember, my end goal here is to factor this polynomial so that I can find when it equals 0. So I'm going to leave the 2 minus lambda factored. I'm going to factor that out of this whole thing. Okay, so when I do that, 2 minus lambda factored out of this and out of this, and what I'm going to get, now I'm going to just multiply out this piece here. I'm going to get lambda squared minus 3 lambda minus 4, and then over here, I get a double negative 6, so a plus 6. Okay, so when I factor 2 minus lambda out of all of this junk, this is what I get. Okay, and this isn't completely factored yet. Like I've got 2 minus lambda times something, I've still got to factor this something. But the point is, instead of having to factor a cubic now, I only have to factor this quadratic. Okay, and I know how to do that. I've got my quadratic formula, and I just know how to factor quadratics. Okay, so first thing I'm going to do, just combine these two constant terms here. Minus 4 plus 6 is 2. And then you factor that. 2 minus lambda is still just out in front from before. And then this quadratic factors as lambda minus 1 times lambda minus 2. All right, good time. So now I know what the roots of this polynomial are, so I know what the eigenvalues of this matrix are. They're 2 and 1, and then 2 again. Okay, so this eigenvalue 2 sort of occurred twice. We'll talk about what it means for an eigenvalue to occur more than one time in a couple videos from now, but for now it's just, hey, eigenvalues are 1 and 2. Okay, so now we're going to find the eigenvectors associated with each of those eigenvalues. And how do you do this? Well, same way as before. Okay, you set up this linear system, a minus lambda I times v equals 0. Solve for v. Okay. First thing you got to do is you got to plug in the particular eigenvalue that you're working with. So I'm going to start off with lambda equals 2. Okay, and that's the linear system that I've got to solve. Okay, so I throw it into augmented matrix form. Here, on the left-hand side, that's A with 2 subtracted off the diagonal entries, right? So if I just scroll back up a little bit, remind you of what A is. If I subtract 2 off the diagonal entries, I'm going to get 0 there, minus 3 there, and a 2 there. And that's exactly what I've got at the bottom here. Okay, so now I solved that linear system. So I'm going to do my row operations to get in row echelon form. Okay, and this matrix, I mean, every row is a multiple of every other row. So my row operations are fairly simple here. And I just zero out all that stuff all at once. I'm just left with sort of one non-zero row here. So one non-zero equation. Okay, if I look at this now, no leading entry, so V1 is free. Yes, leading entry, so V2 is a leading entry, or leading variable. And no leading entry, so V3 is free. Okay, so I get 2 free variables in this case. Okay, so what that means is my solution set is going to be 2-dimensional, right? Remember, it's however many free variables you have. Okay, so my solution set, or my eigenspace, is going to be 2-dimensional in this case. In this case, I'm not just getting a line of solutions, a line of eigenvectors, I'm getting a whole plane of them. All right, but so what is that plane though? Okay, what is the basis of it? Well, I mean, just take this equation here, right? And so this means minus 3v2 plus 3v3 equals 0, and just rearrange that so that it's leading variable in terms of free variable. Okay, so you're just going to get v2 equals v3. Okay, and then write your answer in terms of vectors, right? I want to know what the vectors v are. Okay, well, the vector v has entries v1, v2, v3. What is v1? Well, I just said v1 is free. Okay, so v1 is just itself. Don't do anything there. Don't replace it by anything. Then what is v2? Well, v2 is leading, so I replace it by, an expression in terms of free variables. I replace it by v2 equals v3. And then what is v3? Well, v3 is also free, so it just is itself. Just leave it alone. Okay, so the eigenvectors are exactly the vectors of that form there. And now I want to factor that. Okay, I want to write it as, free variable times something. Here I've got 2 free variables, so the best I can do is free variable times something plus another free variable times something else. So what I'm going to do is I'm going to sort of factor out v1 out of something here and factor v3 out of something here as well. And the way it works is you just look at each entry and you ask, okay, how many of each free variable are here? So for example, with v1, how many v1s in the first entry? Well, there's one of them. How many v1s in the second entry? 0. How many v1s in the third entry? 0. Okay, and now do the same thing with v3, the other free variable. How many v3s in the first entry? 0. And then how many v3s in the other entries? 1 and 1. Okay, so this is sort of the free variable factorization form of my eigenvectors here. Okay, and the point of writing in this form is now we can see a basis of this subspace, of this eigenspace, okay? And a basis is just, well, it's the set consisting of these two vectors here, right? It's a general fact that these two vectors, whenever you do this factoring out of free variables, the resulting vectors are going to be linearly independent. And you can see straight from this formula here that they span the entire space, right? Every eigenvector is of this form, which is a linear combination, right? These are the coefficients, v1 and v3, of these two particular vectors here. So these two vectors form a basis. All right, so our conclusion then is that, yeah, a basis of that eigenspace, it just consists of those two vectors there. Great, so that's the answer for lambda equals 2. We still have another eigenvalue, right? We still have to deal with lambda equals 1. Okay, there's this other eigenvalue. I'm going to leave that for you to do on your own. Similar sort of calculation. This time you're going to find that the eigenspace is just one-dimensional though, okay? And here is one basis of that eigenspace, okay? So the eigenvectors are just all multiples of this vector here. So try that one on your own, okay? Similar sort of calculation, same routine. All right, that was kind of a long one. Thanks for bearing with me, folks. I'll see you next time.